Hi everybody. I just noticed that I didn't set up the chat log panel, so give me a second here. So, normally I do this beforehand, but I apparently forgot today. So, let me do that. And then I gotta make it the right size so that you can see everything, so. There we go. Okay. Oh, excuse me, I had to cough there and mute myself. Yeah, this is Stardew Valley. The premise of the game is basically like you're sick of your life working in like a cubicle, and so you go and inherit your grandfather's farm, and you grow vegetables, and then befriend all 20 villagers who are all bizarre and quirky and adorable in their own way, and have their own like hopes and dreams. And yeah, it's just like a purely like Zen game that I find incredibly what's the word that I'm looking for? It triggers anxiety in me like so badly because there's a timer, and it's called Stardew Valley. Oh, the name isn't. Oh, so if I go back to the title screen, so down here you could see the this is the title of the game that I'm playing the music from, on the title screen, and then during the break when the music's playing. I find it incredibly anxiety-inducing because your character wakes up at like 6 a.m. and then the second you walk out the door, it's 6:10, and then you've walked 5 steps, and it's 6:20, and then it's 6:30, and everything is on a timer. And it's just like, I have to do all the things, because if you don't get back to your bed by like midnight, you start losing like energy that you can use for the next day because you'll be tired. And if you run out of time at 2 a.m., your character just passes out. And it's just, I want to do everything, but I have a limited amount of time, and so I find it very stressful. Whereas it's supposed to be like, just do whatever. You want to garden today? Go garden. You want to go talk to the guy at the bar and like order pizza and then give it to everybody in the town? Like, you could totally do that. I'm like, I want to do all those things and more because I just want to be like super efficient, and I find it extremely harrowing to play. Because I'm trying to cram too much into a day, and like I feel like it reflects my life. So, all right, here we are. We're in the rest of chapter 6 today. What do we have on the agenda? We have lab worksheet number 3 is due on Wednesday, so that is just molecular geometry. Nobody has really had too many problems with that, I don't think. If you have questions about it, let me know in the Discord over email. Happy to answer them. I think that at this point, everybody can do the molecular geometry part just fine. Somebody emailed me about quiz number 5. Apparently, it didn't open. with the answers, so I'm going to look into that. That's not automated. I think I probably just forgot. So I will address that after my 2:30 class today. So at like 4:30 or so, I'll go look into that. And please do remind me if something is closed and it's like, should this be open? I want to study from it, or I want to see my score, or whatever. Like, absolutely, just let me know. I may have forgotten. I have like 75 million students this quarter. All right. So in this last section, what we're going to do is we're going to basically take all of the stuff that we learned in the first two sections. The first one's scrolled off the screen here. And then also this one. And we're going to combine them together. So now you'll get to balance an equation. And then you're going to use that balanced equation to do calculations about chemical reactions. For instance, if I gave you this reaction here, this is how we make ammonia so that we can use it in things like fertilizer. Fertilizer is very important. Plants need a lot of nitrogen. There's nitrogen all around us in the air that you breathe. 79% of the atmosphere is just nitrogen gas. But nitrogen is generally inaccessible to most things. And the reason for that is, if you remember from chapter 4 and 5, if I draw the Lewis structure for nitrogen, I get this. And this triple bond is very strong. I'm going on a tangent here. This isn't relevant to this problem at all. But the point being that plants need nitrogen, but nitrogen in the air isn't really reactive. Those nitrogen atoms are bonded together too well. So we can't use this for fertilizer. It's ineffective. Plants don't like it. Plants don't crave it. But ammonia is much more accessible. And so if we have ammonia or ammonia derivatives, so like ammonium phosphate or stuff like that, plants can absorb that and then utilize that in whatever mechanism or biomolecules that they need to. So we want to make lots of ammonia. So what we're going to do is we're going to study this equation. And we're going to try and do calculations so that we know, okay, if I want this much ammonia in, like, say, grams or moles or whatever, what other stuff do I have to put into our container to get that? So as written, I've balanced the equation. I put this 1 here in green because we don't normally write 1s, but I didn't want to just leave it blank. So I have balanced this equation so that it says that 1 nitrogen molecule will react with 3 hydrogen molecules, and my output is 2 ammonias. Now, you might remember before that we could write a sentence like this. So here's my sentence, and I could write that as a sort of equality for this. So I could say 1 molecule of nitrogen uses 3 molecules of hydrogen, which makes 2 molecules of ammonia. In other words, if I do one of these things, the other 2 are true for this expression. If 1 molecule of N2 is used, I have to use 3 molecules of H2 as well. Or if I use 1 molecule of N2, I will end up making 2 molecules of NH3. Now, all 3 of these are simultaneously true for this reaction. But for any calculation we do, we're only going to use 2 parts of this. We're going to assume that the third one is automatically true and doesn't affect the calculation. Kind of like how before where we had... Let's go over here to do that. Oops. Yeah, this will load. There we go. So you might remember before where we had an expression that looked kind of like this. Where I said 1 mole... 1 mole of P2O5 equaled 2 moles of phosphorus, which equaled 5 moles of oxygen. But for any given problem, we ever really only used, say, 2 of those 3 parts. So if I did something like this, and I wanted to figure out how many moles of O were in there, we would set it up so that our units canceled out like that, right? And then I would just use the coefficients that were there. We're going to be doing the same exact process for this type of problem. Whereas this other thing that we have, it's true, but not helpful for the given problem. So above there, if I wanted to do something like, say, okay, I reacted 50 molecules of N2, and I know that for every molecule of N2 I put in there, I get some number of molecules of NH3 out. And I say, okay, well, I put one of these in and I get two of these out. And I get something like that, right? So it's the same process. Like, what about the hydrogen? Well, we put in enough hydrogen to make the reaction go, but because the problem didn't ask about it, we don't care. That sort of situation. And then the last thing that we're actually going to do is that we don't want to deal with molecules, right? Individual molecules, that's too tiny. So instead what we're going to do is we're just get rid of the C's. So there you go. So 1 mole of nitrogen would react with 3 moles of hydrogen. I don't want to erase the E here because it'll get rid of my L. But it should just say MOL. And when I react 1 mole of nitrogen, I will get 2 moles of ammonia out. And then, once you have that relationship, you could do any calculation we've done in Chapter 6. So there's not actually anything new in this section. It's just a bit of a reshaping of what we did in previous sections to apply it to a chemical equation. So let's play around with this a little bit and see what we can get here. So there's some statements that you could write based on what we wrote before. I don't know why this isn't. Why did it go backwards? That's weird. All right. So let's get a problem here, and let's see if we can answer it based on these relationships. So here's the first one. I don't think that the ammonia reaction shows up here, though, which is strange. So I will just write it in again. So N2, 3H2, 2NH3. All right, so for our example problem here, we're going to react 5 grams of nitrogen, and I'm going to just throw that in with all the hydrogen ever. I won't run out of hydrogen. I have excess of it. I have enough. And it's not relevant to the problem, so we're going to ignore it. In those conditions, how many grams of ammonia can be made? Now, whenever you're given a problem like this, it's important to have enough stuff to react, right? If I didn't have any hydrogen in here at all, then I couldn't do the reaction, right? None of this would actually occur. You would just have nitrogen in a bottle. It can't spontaneously turn into ammonia. So we need to have enough of both things. So the formatting of these problems will always be, here is some substance. I have all that I will need of the other one. Don't worry about it. So we're going to start with whatever substance you're given. So that would be this. So let's go over here again. Oops, that's not going to help anybody. And we'll change back to this color. All right, so I have 5 grams of nitrogen. And so what is my objective here? So the problem is asking me, how many grams of ammonia can you make? Well, what do we know how to do with grams? Well, we can turn grams into moles, right? And if I had this in grams, I could turn it into moles. So those are 2 things that we know how to do. Turning grams into moles is trivial. We can do that. And then, using the balanced chemical equation, I can do this step too. I know that for every mole of nitrogen I put into the reaction, I get out 2 moles of ammonia. So let's set up my units here. so that I can match my little blueprint that I've got going. So I can cancel these units out no problems to turn grams into moles. How do I get the number of grams in a mole? Well, we go to Lentech. Let's go get Lentech on the screen here. I just have to load the page because I closed it. Molecular mass calculator. There we go. Oh, I gotta click up here. So I want to put in there nitrogen, right? N2. So N2 weighs 28.01. Again, here's the link if you need that. And, oops, I can't write on that screen. I gotta write on this screen. All right, so that would be the number of moles, but I don't want moles of nitrogen, so we'll keep the calculation going. We'll turn moles of nitrogen into moles of ammonia. And according to the balanced chemical equation, which should be right up above here in red here, that you could see, for every 1 mole of N2, I get 2 moles of NH3 out. And I'm just taking the coefficients. These coefficients right here. So this is a 1 in this blank, and this 2 right here. That's still not the units that I want, though. I want to get a mass of this. Oops, I wrote the wrong letter for some reason. And then again, how do I do grams per mole? Well, I just go to Lentech and type in NH3. Because we are too busy to bother adding up numbers on a periodic table. And that is okay. I can accommodate that. There you go. So now we just punch all this into the calculator, which I did have set up here. So 5 times 2 times 17.03. Now notice what I'm going to do here. Be very careful about this. When you go divided by, use parentheses, and then multiply all the numbers on the bottom together. Now there's only one number here. So if I do 28.01 times some other number, it'd be important to have the parentheses, but I just do it out of habit. And then there's our answer, 6.08. Now, you might look at that number and go, okay, that's a number. But wait a second, I put in 5 grams of nitrogen. How the heck do I get 6.08 grams out? And the answer is, well, the remainder must be the hydrogen that was added. If 5 of those grams were nitrogen, you reacted this with an extra 1.08 grams of hydrogen because you have to follow the conservation of mass, right? So even though the hydrogen is not being a part of solving this problem, it does exist. So you aren't actually violating the conservation of mass by getting a number that's bigger. Like, where did this mass come from? That's because we did a reaction behind the scenes. So that's how you do this type of problem, and it shouldn't be any different than the problems that you've done earlier in this chapter. This is really just the new part, and we want to do this by using the equation for a given problem. If you don't have a balanced chemical equation, you definitely need to balance it. Otherwise, you can't get these numbers. So it's essential that we're working with a balanced chemical equation, or none of this works properly. Oops, sorry. There we go. All right, for the next problem, what I want you to do is I want you to tell me how much ammonia, or not ammonia, I'm sorry. Tell me how much nitrogen you need to insert into the reaction flask in grams if you're also adding 2.75 grams of hydrogen. So what amount of nitrogen is required to completely react with your 2.75 grams? How much ammonia do you make? Doesn't matter. We're not asking about ammonia here. Do I have the equation in this slide? Did I put it up here for you? No, I didn't. So we'll write it in here again. All right, so I would like you to solve this problem. Tell me how much nitrogen is needed in grams. going to do it the exact same way as the problem we just did. So give it a shot. Give you 5 minutes. We'll go over the answer when I get back. Let's do 2 more minutes and we'll go over the answer here. All right, let's give this a try here over on this screen. I have a red dot on my... Oh, it's because I had a window selected. Okay. It's like, I don't know what that means. All right, so I'm given a mass of hydrogen. And that is this. And what is my objective here? Well, I'm starting with grams of hydrogen, so we'll write that down. And my objective is I want to know how many grams of nitrogen are needed. So we would need this. Now I got to connect these two so I can get from one to the other. So I'm going to turn both into moles here. Moles of H2. I can turn this into moles of N2. Or more appropriately, I can turn it back into moles of N2. And then I just connect these two using the balanced chemical equation. You're going to notice that for all these types of problems, you could turn the starting point and the ending point, you just turn them into moles. And you have to, right? Because they're all dead ends on that little chart that we have here. So if I started on my chart down here, and this is my goal, there's only one connection to these places, so I have to do something like this, right? And then I just connect them together. So that's what we're doing when I'm writing these little charts out in like blue or purple or whatever. So let's do that. Let's follow our blueprint here that we've got. So I've got, oops, that's the wrong color. Hold on. There we go. So we got grams of hydrogen, which will turn into moles of hydrogen because we're just following the blueprint we made. And then I got to go look up how many grams there are in a mole of hydrogen. It's like 2 point something, right? Yeah, I think that's right. That's close enough. I didn't actually look it up. I'm just using my memory. Now I'm gonna be upset if I get it wrong. So let me grab a periodic table here. 10079. So 2016. Yeah, that's right. Okay. Trying to do mental math. All right. Next step is moles of hydrogen to moles of nitrogen, so we'll do that. And this requires us to look at the balanced chemical equation above, so I know that when I put a nitrogen in, I must also put in 3 hydrogens. So that'd be true if there were moles, right? 1 mole of nitrogen would require 3 moles of hydrogen. So that checks out. And then finally, moles of nitrogen into grams of nitrogen. And in 1 mole of nitrogen, there are still 28.01, was it? Yeah, 28.01 grams. And so now we'll do our calculation here. So 2.75 times 1 times 1 times 28.01. I'm just ignoring the ones here. Divided by parentheses. Make sure you use your parentheses here. Real important. 2.016 times 3. And then I'm going to hit enter, and I get 12.7 grams of nitrogen are also needed. Now, the reason that we need the parentheses when we're doing this in the calculator is because you're dividing by both of these things. And if you type it in the calculator like this, where I go 2.7... Oops, hold on. Oh, no, I've ruined everything, haven't I? I turned the opacity to some other number. So hold on, let me get the pen back to what it was. Oh, no, that's not what it was at all. Okay, hopefully I fixed it. Yeah, that looks good. Okay. Sorry, when I type on the number pad, if I don't click on the calculator and I'm clicked on Photoshop, everything goes away. So if I did the calculation like I had just done, but I don't use parentheses, here's what happens. The calculator thinks that you want to divide by 2.016, and then it thinks, okay, I'm going to take the number of those 3 steps that we've just done and hit enter. And then when I type times 3, it's going to times the result of all of these numbers that we typed in, which would have been these at this point. And it's going to multiply that by 3, which is obviously not what you want. You want to divide it by 3, right? So if I hit times 3 here, I get an answer that's way too big, where in reality, we'll undo that. I wanted to divide by 3, and you'll notice that I get the answer that we're supposed to. So use parentheses around any bottom numbers, and then just multiply them together. Well, let me get rid of this little circle here. There we go. So if you ever don't get the answer that I get when I'm doing these calculations, check for parentheses. Put parentheses around the thing on the bottom. And if you're concerned, you can put parentheses around the thing on the top too. That's fine. You can't ever have too many parentheses, provided that you aren't putting them in the wrong spot. So just be careful. All right, let's have you do one more. And then we'll be done with Chapter 6, because this is all there is. So we're going to give you a new reaction. This is sodium azide. Sodium azide is industrially relevant because... Or not industrially, but commercially relevant. Because we use it in your car. What sodium azide does is it follows this formula. And let's draw a picture. Let's teach you about airbags. An airbag is a tool that is used to keep you from crashing into your steering wheel. Before airbags were invented, people would bonk into their steering wheels and suffer grievous injury. Like, that's the last thing I want, is to hit my face on the steering wheel of my Jeep. Like, holy shit, that would hurt a lot, right? So, here's my Jeep, which is basically a cube, right? Because that's what Jeeps look like. And like all Jeeps, the back wheel is bigger than the front wheel. And then the wheel on the very back is the biggest. Here's my steering wheel. And I have a bumper on my car. Those are actually both relevant, and you'll see why. The steering wheel is connected to the steering column, which inside has an airbag. And all of this is connected by a tube to a chamber that has sodium azide in it. So there's our sodium azide. So believe it or not, this is in your car, sodium azide. And what this is all connected to is connected to a circuit, which is connected to the bumper. And the way that this works is that if something impacts the bumper with enough force that it causes the circuit to activate, if the circuit activates here, then this is ignited and it decomposes. And what does it make? Well, it turns into sodium metal, which is very reactive, but fortunately there's only a little bit of it in there. And it also produces nitrogen gas. Well, nitrogen is a gas, so it fills up the space that it's trapped in, and it expands this way, which is your steering column. Then it hits this thing, which is the point of least resistance, and it goes foomp, and it fills the airbag. Hopefully not that much, because I would be like, ah, and pushed into the trunk of the car. But it produces a lot of gas, and it produces it extremely quickly. And that's relevant because if you impact something at a very high velocity, you're going to go careening right into your steering wheel. And so we need to fill that with some sort of gas extremely fast. If you got 12.8, that's fine, JY. Yeah, totally okay. So our nitrogen fills in here. You impact the airbag, which can still hurt. I mean, hitting anything at a high velocity is going to cause pain and or injury. But it's not going to hurt as much as you hitting a solid steering column. All right, so let's go back to the problem. Now that we know how an airbag works, I would like you to tell me how much sodium azide would I need to decompose to create 253 million molecules? You might think, oh, that's a lot of molecules. It turns out it's really not. 253 million molecules is a rather small number, it turns out. Now, in this instance, I have given you a number of molecules as your starting value. So you're going to start with this part on the chart here. But I still want a mass at the end. So treat it in the same manner. Do the same sort of procedure here. It's just that how do I get from molecules to moles? What number do you use? Could it be a famous number? Anyway, I'm going to give you 5 more minutes to try that one too. And then we'll go over the answers in just a bit. By the way, when you're done with this problem, you should get a really tiny number. Let's do 1 or 2 more minutes, and then we will go over the problem. All right, let's go over the solution. So let me just put the relevant stuff on the screen here. In the wrong window. There we go. We can get rid of that. All right. So I am given a number of 253 million, which is just... That's not a 3. To the 8, right? Yeah. So I was given a number of molecules. And my goal for this problem was to get a mass in grams of NaN3. Whenever I ask you for mass for these problems, just always do grams, because those are the units that we use for masses in chemistry, basically. So I can turn this into moles. That shouldn't be too hard. And I can turn this back into moles. I'm thinking ammonia. There we go. NaN3. And I can just connect the two using the balanced chemical equation, right? So let's do that. I'm going to kind of run out of space, so I got to do it this way. How many molecules are in a mole? How many anything is in a mole? Well, in 1 mole, there are Avogadro's number of things, right? Then we can use the balanced equation, and we could say, okay, well, I'm going to use, for every 2 moles of NaN3 I put in there, I get 3 moles of N2 out, right? Where did I get those numbers? Those are from the balanced chemical equation right here. So this is my 2 for NaN3, and this is my 3 for N2. The sodium part we don't really care about because it's not part of the problem. It is used in the background, but we're not actually calculating it. And then finally, we'll turn moles of sodium azide into grams of sodium azide. And according to Lentech, the molar mass of sodium azide, NaN3, is 65.01 grams per mole. And so now I got to type all this in the calculator. And I should get a tiny number, right? 2.53 times 10 to the 8 times 1 times 2 times 65. Oh, crap. Sorry, I hit plus. Let me try that again. Times 2 times 65.01 divided by parentheses 6.022 times 10 to the 23 times 3. Close the parentheses, enter. And I get 1.80 times 10 to the... Oh, sorry, 1.82. Skipping numbers on the calculator there. 1.82 times 10 to the minus 14 grams. So if you wanted only 253 million molecules, you need like a speck of NaN3, smaller than you could see. How did I get the 65.01? I actually have that on the screen here. So the 65.01 grams per mole is from this. Ooh, that's... Oh, I gotta click over here. Why is it showing that? That's weird. Hold on. It's showing my cursor. NaN3. Oh, that's strange. It has like the old version of it. Hold on. Yeah, there we go. Now it's showing the right thing that I had in there. So I typed in NaN3. What does it weigh per mole? And it's this much, 65.01. I'm confused about Avogadro's number. So whenever you have a number of things, you can tell me how many moles that is by using Avogadro's number, right? Because in 1 mole of something, there are always Avogadro's number of that thing. So if I have a count of molecules, which is what this is, right? I can turn that into moles by converting from molecules to moles. Because remember that this is always true, right? 1 mole of anything equals Avogadro's number of that thing. And when I say units, I mean like individual, like discrete things that you could count. So if I had a mole of marbles, I would have 6.022 times 10 to the 23 marbles. If I have a mole of molecules, I have 6.022 times 10 to the 23 molecules. And so on. It's true for anything. So regardless of what the identity of the substance is, in 1 mole there are that many of that thing. That many as a counting is what I mean. So to get to mole, you use Avogadro's number. If you start with molecules or particles or something like that, then yes. So you follow this process if what you have is a counted quantity. Which we did, because it was molecules. Grams is not a counted quantity. You don't count 1 gram, 2 gram, 3 gram, 4 gram, or whatever. But molecules you do. Hopefully that helps. We're going to take a break right now, so if you have more questions, you can always ask me during the break. I'm just going to sit here in the chat and hang out, so... we will reconvene in about 10 minutes, so please take a short break to refill your water. Let me get the timer on the screen here. Yeah, do I want to update? No, never update anything. And we'll start this, and we'll get some more music going from Stardew Valley, so see you in just a little bit. There we go. I forgot to set up the next slide here. Alright, so this is the next slide after. And what I want you to do is I want you to solve this problem, but there's a very important thing to note here, and that is I didn't balance the equation. So you got to do that first, okay? Don't jump into the problem just assuming they're all ones, because you could see, oh, I lost oxygen, right? So that's not balanced. So first step, balance your equation. And then step 2, I'm going to give you 0.522 grams of KClO3. We're going to react it completely. How many grams of KCl are left after the reaction is done? So tell me that, and then in the second question, tell me how many grams of oxygen are produced from the same reaction. So you do 0.522 again. And then look at your two numbers afterward and tell me, has the conservation of mass been verified? In other words, is what I started with equal to however many grams of KCl I made and however many grams of O2? And guess what? It should be, because we're doing chemistry, right? I can't destroy matter. So if I figure out the mass of both things, I should get the same result before and after I've added them together. So figure out these numbers individually. So here you're going to figure out grams of KCl. Here you're going to figure out grams of oxygen. And then add your two answers together and see if they equal this number. And they should. So I'm going to give you like 5 or 6 minutes to do both of these problems. So you do have to work a little faster. But other than that, that's at the end of chapter 6. So go ahead and do this last practice problem. And we'll get set up for chapter 7 after we go over the answers. So see you in a bit. I was talking. Can you hear me now? I'll just type into the chat what I meant to say, just in case you can't hear me. Let's do 2 more minutes and we'll go over the answers. All right, we're going to go over the answers here, but I want to make sure that Kate can hear me. So going over the answers now, so you should hear me talking. There we go. Just in case it's still not working on her end. So I'm going to balance the equation real quick. And I need my pen to do that. So this should be 2, 2, 3. So that should be what you got for balancing the equation. And then we'll go over here and get rid of all this. And all right, so we have 0.522 grams of KClO3. And I want to figure out how many grams of KCl I have at the end. So we can turn both of these into moles and then just connect the two. Oops, I hit the wrong button. There we go. So let's do that. So we'll go grams KCl. Oops, I messed up. Hold on. KClO3. Moles KClO3. And according to Lentech, how many grams is that per mole? Let's see here. KClO3. All right, so I got in 1 mole there are 1, 2, 2, 5, 5. And then when I do moles KClO3, so moles of KCl. And according to our balanced chemical equation, which I have covered up by Lentech, hold on. For every 2 moles of KClO3 I put in, I get 2 moles of KCl out. And then finally, moles of KCl over grams of KCl. And in 1 mole, how many grams are there? Well, we'll Lentech that too. So we'll just... Why is this not clicking? There we go. KCl is 74.55. And then we'll calculator. So 0.522 times 1 times 2 times 74.55 divided by parentheses 122.55 times 2. Close parentheses. So that's what I got. 0.317 grams of KCl. For the next one, we'll do the same thing with our starting amount, but we're going to calculate oxygen. I got to move my phone here because it's in the way. Don't know why it was sitting on my tablet. So this time, we're going to go from grams of KClO3 to... I really need to move this calculation down a little bit. There we go. We're going to go to grams of oxygen. We're going to solve the problem in the same way. We got the 2 from the balanced equation. Yeah, exactly. So these 2's came from the equation that is at the top here. I can't actually draw on it from the screen, but it's way up at the top. I do need to scroll this a little bit because I need to be able to write down here. You can pause the video and rewind. So we'll go like this. So grams KClO3 to moles of KClO3. And this is the same as above, 122.55. And then we'll do moles of KClO3 to moles of O2. And then we'll use the balanced chemical equation for that. So for every 2 KClO3s that I put in, I get 3 moles of O2 out. Now I've kind of run out of space, so I got to continue down here. Then we can do moles of O2 into grams of O2. And in 1 mole, according to Lentech, it's 32.00 grams of O2. And so we'll punch all that in the calculator to get some mass of O2. And so I get 0.522 times 1 times 3 times 32.00 divided by parentheses 122.55 times 2. Not 21 times 2. There we go. That's what happened. That's way too big. Oh, I see what happened. Okay. Sorry, hold on. I had a divided by in there when I didn't want one. 32.00 divided by parentheses 1.22 or 122.55 times 2 close parentheses. There, that's what I wanted. Okay. 204. So you have to balance the equation first. Yeah, if you don't have the balanced equation and you put all ones in there, you get the wrong answer. So remember, always have a balanced equation. If you don't, the problem falls apart. All right, so now the last part of this question is, has the conservation of mass been verified by this experiment? So we're going to look at that. So I've got, here's my KCl, and then here's my oxygen. So we'll just add them together. And what you'll notice is that when I add these together, I had an answer that's extremely close to what we started with. So we have indeed verified the conservation of mass. They are essentially the same number. The small difference is going to come from like sig figs and rounding. We learned to balance the equation in the lecture last week for chapter 6. Yeah. It was the most recent lecture. So that would have been Thursday? Thursday, week 6, yeah. All right. There you go. That's chapter 6. We're all done. We did it. Hooray. There's the homework practice at the bottom. There's tons of problems here. Do as many of these as you can because it's good practice. And then we get celebrate because that's the worst of the math behind us, at least in my opinion. So hooray. All right. Screen will go blank for a second because I need to load the correct slides here. So we'll get rid of chapter 6. And we'll get chapter 7. There we go. Okay. All right. Chapter 7 is a different topic. It is on phases of matter. We're going to spend the rest of the day talking about gas laws. Yeah, chapter 6 is the worst chapter, I think. This chapter is a lot easier because we're going to use very simple equations. We're just going to multiply and divide numbers together. So today we're going to watch a bunch of videos about gases, and we're going to see how gases behave. So the first thing that we want to talk about is how energy is stored in molecules that are moving. So, for instance, in the air that you are breathing right now, the molecules that are moving around in the gas phase have energy to them. So, for instance, let's suppose that I'm drawing a picture of the particles in, I don't know, say a room. So here's my room, and it has several air particles in there. And all of my air molecules are moving around, bouncing off of other things, and so on and so forth. So they all have momentum. So the ability of molecules to move is what we call kinetic energy. Kinetic energy is the energy of motion. If you throw an object at, like, say, a wall, and it hits the wall, you might dent the wall. Or it'll bounce off it and make a loud sound. Or it might even go through the wall if you have a big enough object, like a wrecking ball. The energy that objects have when moving is kinetic energy. And the faster something is moving, the more kinetic energy it is. So, for instance, if you have a car, and the car, like, drives into, I don't know, like an object that can be moved, the object will then suddenly start moving because the car had energy that then transferred to the object. I guess a better example would be like billiards. If you hit a billiard ball on a pool table, and that ball hits another ball, the other ball starts moving, and the first ball might stop, depending on how you hit the ball. So, that's all kinetic energy. Now, what is potential energy? Potential energy is the energy that something has based on where it is. So if I have a table, so here's my table, and it is sitting on the ground, of course. So this is a table. And I have an object on the table like this, and I have another object on the ground. This object will just sit here. And it will have no potential energy because it has nowhere really to fall to. But this object, if it is like bumped over by, say, like a cat, then what will happen is the object will then go, and it will fall, right? I wanted to draw that as a dotted line. Well, actually. So this object has the potential to fall and have an impact with the ground. So that energy had to come from somewhere. The object, if it rolls off the table and hits the ground, that energy comes from it accelerating into the ground due to gravity, right? So we say that it has the potential to provide energy. In other words, it's potential energy. So potential energy is from things like an object is sitting on a high area and then it falls to the ground. But it's also for things like I have two things that are magnetically attracted together, and then I let them go and then they attract. So like if you've ever held a magnet like up to your fridge, but not on the fridge itself, like you have it a distance away and you could feel the magnet pulling towards the fridge, and then you let it go, that energy doesn't just come out of nowhere. That energy is potential energy. It has the potential to turn into kinetic energy. If you throw a ball upward, the ball will slow down and will stop rising, right? That's because your kinetic energy, which is the energy of motion, is turning into potential energy. So if like I launch a ball like this, at its peak, there's no kinetic energy, and it has all potential energy. It has potential to fall back down. When it's moving, it has all kinetic energy and no potential energy. So the gist here is that if you're moving, it's kinetic energy. And if you're not moving, you're just stuck in some position, it's potential energy. Now, the potential energy is going to depend on the circumstance, right? If something is just sitting on the ground, there's no potential for it to fall further or move in any direction, then it has no potential or kinetic energy. Now, what does this discussion mean for molecules moving around? Well, gas molecules move around like crazy, so they have lots of kinetic energy. They don't have any potential energy, though, because that energy has already been used to make kinetic energy. But if the molecules instead were, like, say, trapped in place, like, say, as a solid, in the solid state, all of our molecules have potential energy. If we were to get them out of the solid state by like breaking their bonds or something, then they would all fly around too, and they would have kinetic energy. So the potential energy is stored in things like bonds and stuff. So we can separate out our three phases by talking about which phases have the most kinetic energy and the most potential energy. So let's talk about the three phases, solid, liquid, and gas. Just like we did at the very beginning of the quarter, we're going to define them in terms of kinetic energy. And this is called the kinetic theory of matter. Solids have atoms that are basically stuck in place, right? So if this is my solid, my atoms are essentially stuck, right? Because solids don't move around. They don't change shape. They don't flow. They're just rigid. So the atoms are essentially stationary. They're stuck in place. So they can't have kinetic energy. But they could. They could have kinetic energy if it weren't for whatever bonds are holding the molecule together. If those interactions were gone, then the atoms could move on their own, right? So they instead have potential energy. Now, a gas, like we said on the previous slide, gases are just all kinetic energy because they're just moving in any given direction that they want to at any given time. So because gas particles can move all over the place in any direction they want to, they have high kinetic energy. And because there's nothing holding them back, they have very little potential energy. Liquids are kind of in the middle, and my liquid's going to appear in the middle here. Here's the Kool-Aid Man. Liquid molecules can move around, but they can't move in any direction they want to. For example, the liquid molecules in the Kool-Aid Man's pitcher can't move in this direction, right? They would escape the container and it would no longer be a liquid, it'd be a gas. So we would say that they have both potential and kinetic energy, and they're about the same. So, in other words, what we can do is we can make a little table here. So let's do that real quick. So for solids, we have low kinetic energy and high potential energy. For gases, we have high kinetic energy and low potential energy. And then for liquids, they're roughly the same. The stronger the bonds, the more potential energy. That's correct. So something with incredibly strong bonds, like say like a diamond, would have the highest potential energy. It would have the lowest kinetic energy. So something that's melting would be gaining kinetic energy at the cost of its potential energy. So the potential energy would turn into kinetic energy. Oh, I need to pause real quick. There is a knock at my door. So be right back. Hi, sorry about that. I have a maintenance request for part of my patio, and somebody just came by to do it. Of course, they came by right during class. So we'll go back here. All right, so that's our just table of differences between kinetic and potential energy. So we can describe phases like that, and that's going to be less important for the solid phase, but most important for the gas phase. So there's our summary, and the bottom section down here, there's some homework questions that'll ask you about like which molecules can move, therefore which have kinetic energy, and so on and so forth. All right, so we're going to move on to the gas phase, and we're going to extensively talk about that over the rest of the lecture, which is only like 10 more minutes. But so we're going to watch some videos about gases and various properties that we can manipulate. But to start with, what I want to do is we want to try and figure out what properties of a gas can be measured. So in order to do that, we're going to draw a picture. Let me just get this on the screen so we know what question we're asking here. And so let's draw a picture of a gas. So I'm going to have a chamber like this. And my chamber's going to be closed so that the gas can't escape. And so what I'm going to do is I'm going to just put a bunch of particles in here. And we're going to assume that all these particles are just moving in random directions. So like this, like that. This one can just go this way. Maybe this one hits that one. I don't know. That one's having a rough day. I don't know. So our molecules are all moving at different speeds and angles and all over the place. They're hitting each other, they're hitting the walls, etc. So my gas is defined as all of the particles within the box. Oops, there we go. I got a little off course there. So if I wanted to measure specific properties of these, what could I measure? So the first property that we're going to measure is, well, what do gases do? They fill the container, right? So the first property we're going to measure is the volume. The volume is just how much space the gas occupies. So if I had like a 1 liter bottle and it was completely full of, say, oxygen, the volume of the oxygen gas would be 1 liter, because that's the volume it occupies. What other properties could I measure? What is the impact of when molecules hit the side of the container? When molecules strike a surface, their kinetic energy rebounds off of that surface. And if you have tons and tons and tons and tons of molecules doing that at every given instant, they exert a force of their own. And this force is called pressure. And that is the force that is exerted by the molecules on whatever surface of the container you have. Now, another feature that we talked about was molecules have kinetic energy. How fast are the molecules going? If molecules are going faster, they have more kinetic energy. If they're going slower, they have less kinetic energy. Believe it or not, this is a phenomenon that you're familiar with, probably right now, as it's starting to finally get warmer. The temperature of a set of molecules is simply how fast they move. Or in other words, how much kinetic energy they have. If molecules have more kinetic energy, they move faster. And if they move faster, we interpret that as, oh, it's hotter. So if you go outside on a winter day, the molecules are moving slower. And when they hit your skin, you go, oh, that's cold. Brr, it's freezing out. But if it's a really hot day, the molecules are moving faster. Is that why there's less oxygen in water when it's warm outside? That's exactly why, yeah. Because oxygen moves faster, and therefore it dissolves less easily in water. It's easier to dissolve gases in water when they're moving slower. And then finally, I need more space here. We could count the number of molecules. And we're going to count that in moles because that's just the unit that we use. So you'll notice that I have 4 variables here that I've written: V, P, T, and N. And these are going to be very important to us as we talk about gases. So these are the 4 properties of gases that we can measure and define. So if I have a container that has gas in it, that gas will have all these properties. All right. So let's talk a little bit more about some of these properties here. So we've already defined these. I want to talk more about pressure so we can define this. So you've heard of air pressure or atmospheric pressure, or you might have, maybe you live or have lived in, say, the southeast of America where you get hurricanes all the time. You hear about air pressure fluctuations and how hurricanes have a center of very low air pressure, which causes stuff to whirl into them. And so what does all this mean? So where does air pressure come from? Air pressure is basically the effects of gravity on air. all matter, including gases, is subject to gravity because it's all mass, right? And all mass is attracted to other mass. The Earth is our big mass, and so everything is attracted to the Earth. This includes air. Now, if I draw a 1 square meter region on the ground and I extend that 1 square meter area all the way up to the edge of the atmosphere, I get a giant column of air that is being pulled down. And this column of air is being pulled down on top of you right now. And it has a mass of approximately 10,000 kilograms. So right now, if it feels like you have the weight of the world on your shoulders, well, you don't, but you do have the weight of 10,000 kilograms of air pushing down on you. So next time somebody says, "Do you even lift, bro?" you can say, "Yeah, 10,000 kilograms every second." But so do they, so it's not really much of a claim, because our bodies have evolved to adapt and acclimate to that air pressure. Now, we're going to define the force of this column of air at a specific location. And the location that we are going to define that at is sea level. So if I have something at sea level, because right in the middle of, like, say, I don't know, South Dakota is where I would put this marker, or North Dakota. That's definitely sea level, right? No, it's not. Oh my goodness, the door knock again. So this is atmospheric pressure. I'll be right back again. I'm so sorry. All right, sorry about that. I'm back. Hopefully that won't happen again. Okay, where was I? So we're going to define atmospheric pressure as the mass of this amount of air pushing down on you if you were at sea level. So that's going to necessitate another diagram here. And this will probably be the last thing we have time to talk about here. But let's say that this is the atmosphere. Our atmosphere is purple today. And then here's the sea. So you actually do feel it. And we're going to talk about how you feel this. So here's, I don't know, so this might be like, say, Washington or Seattle or Everett or whatever. And then maybe you go inland or something, and so you go onto a mountain. And this is all exaggerated. So this could be like Mount Rainier. If you're standing here at sea level in Seattle, then you would feel 1 atmosphere of pressure. But let's suppose that you go on an airplane. And in order for my airplane to really work, we're going to have it be like up here or something. So here's my airplane with its propeller or engine or whatever. And it's zooming along. What do you feel when you go in an airplane and you go all the way up to the cruising altitude of like 35,000 feet or whatever? Really high. You feel something, don't you? And what you're feeling is the reduction in pressure from the gas that is above you. And just in case you aren't sure what you're feeling, the most common symptom I had this when I was a kid, is it's in your ears, right? Your ears pop. And you have to do the or you like like chew gum, or you do something to try and equalize the pressure. So when the plane goes up, you feel the change in pressure on your ears. And there's cabin pressure inside the plane, but it's not 1 atm. It's not as much. Otherwise, the air pressure of inside would push outward and buckle the plane, and we obviously don't want that. So the end result here is that we're used to this. This is normal. This is not normal. And we feel it in our ears. And we're going to talk about that a little bit more on Wednesday when we come back to this. The other way that you would feel this is if you are in a location where there's more pressure pushing down on you. For example, if you go swimming down here in the sea, then not only do you feel the pressure of the atmosphere here, you feel the pressure of water. Have you ever gone swimming and swum down to like the bottom of a pool? And you're like, holy crap, that hurts my ears. Your ears are very sensitive to pressure. And the reason for that is because not only are you feeling the weight of the atmosphere at that depth, you're also feeling the weight of the water above you. And water's way more dense than air, so it affects you much more severely. So we do feel all of these differences in pressure, but the sensor is not what you would have actually thought it to be. Like, you don't feel it with your arms or your stomach or anything like that. You feel it with your ears. It's your eardrum. Because your eardrum is very, very thin, and it interacts with the world by air hitting it. That's how we get sound. Sound is just vibrations of molecules, right? Now, the last thing I want to talk about before we go is that pressure relative to the surface is going to be important for us when we talk about boiling. So here we have 1 atm pressure because we're at sea level. If we're at an elevation that's not sea level, so like say you're up here, like you live on the side of a mountain, then the pressure that you would feel at that distance would be less than, or not surface, but you'd feel, the pressure you would feel here would be less than that you would feel at sea level. And so that's going to have implications that are relevant for us when we start talking about things like boiling. So keep this diagram in mind. We'll draw it again when we get there. All right. When we come back on Thursday, we're going to watch a bunch of videos about gases. We're going to explore some different properties that we can measure of them. And then we will do some calculations so that we can predict various properties of gases. And the calculations shouldn't be that hard because I give you these formulas. You just plug in the numbers. So it should be okay. All right, I do want to thank everybody for coming out to the lecture. Make sure that you get lab worksheet number 3 in by Wednesday. It closes 24 hours later on Thursday. So be sure to get it done by those times. And when we come back on Thursday, we will be doing more gases and stuff and solutions. So yeah, make sure you stay on top of that. Ask me any questions you might have in the Discord. Send me an email if you need to. And we'll see you on Thursday. Go enjoy the nice weather that's coming up. Take care.